Take a deep breath and allow your shoulders to drop, feeling the weight of your body sink into the soft, steady support beneath you. As you exhale, let the busy thoughts of the day dissolve into the cool, quiet stillness of the upper atmosphere, where the air grows thin and the stars begin to shine with a steady, unwavering light. On September 5th, 1977, a journey began that would redefine our understanding of distance and solitude. On that humid morning at Cape Canaveral, Florida, a Titan IIIe Centaur rocket ignited, carrying a small, sophisticated craft named Voyager 1 into the sky. It left the Earth at a staggering speed of approximately 38,000 miles per hour, a velocity that allowed it to escape the gravitational pull of our home planet and begin a trajectory toward the outer giants of our solar system. Imagine the sensation of that departure, the immense controlled power of the engines transitioning into the sudden, profound grace of weightlessness. This was not just a machine being launched, it was a sensory extension of humanity, a set of eyes and ears designed to drift through the eternal evening of the cosmos. Within the first few minutes of its flight, Voyager 1 shed its protective fairings, revealing its iconic silhouette against the blackness of space. The craft is built around a 10-sided aluminum bus, a sturdy metallic heart that houses the most vital electronic components. Imagine the texture of that aluminum, cool to the touch, polished, and resilient. This central housing is just under 6 feet across, yet it contains the logic and memory that have guided the mission for over 4 decades. Remarkably, the total computer memory on Voyager 1 is only about 68 kilobytes. To put that in perspective, a single low-resolution photograph on a modern smartphone would be thousands of times larger than the entire digital mind of this interstellar traveler. There is something deeply comforting in that simplicity. It is a testament to the elegance of 1970s engineering, where every single bit of data was precious and every command was a carefully weighed instruction. As we drift alongside the craft, you might notice the large, white, dish-shaped object that dominates its profile. This is the high-gain antenna, measuring 3.7 meters, or about 12 feet, in diameter. It is the craft's mouth and its ears, a parabolic curve designed to focus radio signals into a narrow, concentrated beam. In the silence of space, this antenna is constantly oriented toward a tiny flickering point of light, Earth. Even now, as Voyager 1 has traveled over 15 billion miles away from us, it continues to whisper back to the deep space network. Because of the vast distance, a radio signal traveling at the speed of light takes nearly 23 hours to make the one-way trip from the spacecraft to the receiving stations in California, Spain, and Australia. Consider that rhythmic delay, a slow, nearly day-long conversation between a lonely traveler and its home, a pulse of information that crosses the void with the patience of a shifting tide. Floating near the central body of the craft, you would feel a gentle, radiating warmth, a stark contrast to the minus 455 degrees Fahrenheit of the surrounding vacuum. This warmth comes from 3 radioisotope thermoelectric generators, or RTGs. These are not solar panels. Voyager 1 travels far too deep into the shadows for the sun to provide meaningful power. Instead, these generators use the natural radioactive decay of plutonium-238. As the plutonium atoms break down, they release heat, which is then converted into about 400 watts of electricity, roughly the amount needed to power a few light bulbs. This nuclear heartbeat is a slow, steady simmer, a glow of warmth that has sustained the craft's instruments for 46 years. It is a quiet, internal fire, keeping the electronics just warm enough to function in the freezing dark. Attached to the side of the craft is perhaps the most poetic object ever constructed by human hands: the Golden Record. It is a 12-inch gold-plated copper disc, and protected by an aluminum cover that has been electroplated with an ultra-pure sample of the isotope uranium-238. If you were to run your fingers over the cover, you would feel the etched diagrams, the pulsar map showing Earth's location in the galaxy, and a symbolic representation of a hydrogen atom. Inside, the record contains the sounds of our world: the rhythmic patter of a thunderstorm, the low croak of a frog, the laughter of a child, and the intricate melodies of Bach and Mozart. It is a time capsule of our collective senses, a message in a bottle cast into the cosmic ocean. The record is designed to last for over 8 billion years, meaning that long after the mountains of Earth have crumbled into the sea, the sound of a human heartbeat will still be engraved on this golden plate, drifting through the stars. As Voyager 1 moved past the Moon and into the deep velvet of the inner solar system, it relied on small, precise thrusters to maintain its orientation. These thrusters use a chemical called hydrazine. When the hydrazine passes over a catalyst bed, it decomposes into hot gas, creating a tiny, gentle puff of pressure. These maneuvers are not violent. They are delicate adjustments, like a sleeper shifting slightly in bed to find a more comfortable position. Even now, decades later, the craft occasionally uses these thrusters to keep its antenna pointed exactly at Earth. There is a profound sense of dedication in these tiny bursts of gas, a machine refusing to lose its connection to the world that made it. Consider the visual journey of those early years. In 1979, Voyager 1 made its closest approach to Jupiter, becoming within 217,000 miles of the planet's swirling marbled clouds. It captured images of the Great Red Spot, a storm 3 times the size of Earth that has been raging for centuries. The colors were a palette of ochre, cream, and deep crimson, composed of complex gases like ammonia and methane. The craft's cameras, which are now turned off to save power, revealed that Jupiter's moon, Io, was a world of violent volcanic activity, covered in yellow sulfur and jagged peaks. The sensory reality of Io is one of extreme heat and extreme cold, a landscape of frozen gases and molten rock. Voyager 1 moved through these environments with a stoic, observational grace, its sensors measuring the intense magnetic fields of the gas giant, which are 14 times stronger than the magnetic field of Earth. By 1980, the traveler reached Saturn. Gliding past the majestic rings, which are composed of billions of individual pieces of ice and rock, ranging in size from a grain of sand to a massive mountain. Voyager 1 discovered that these rings are not solid sheets, but a complex rhythmic dance of particles influenced by the gravity of Saturn's many moons. The craft's photopolarimeter instrument measured how the rings blocked the light from distant stars, revealing their intricate braided structure. The temperature in the vicinity of Saturn's rings is a numbing -300 degrees Fahrenheit, a crystalline environment where light reflects off ice with a blinding diamond-like brilliance. Voyager 1 felt the tug of Saturn's gravity, using the planet's orbital momentum to slingshot itself upward and out of the plane of the ecliptic, the flat disk where all the planets reside. And this maneuver changed the craft's path forever. It began to climb north, away from the orbits of the planets, heading toward the boundary of the Sun's influence. In February 1990, as it reached a distance of 3.7 billion miles from the Sun, Voyager 1 turned its camera back toward home one last time. It captured a sequence of 60 frames that would become known as the Solar System Family Portrait. Among these images was a single tiny speck of light caught in a scattered beam of sunlight. This was the pale blue dot. From that distance, Earth was less than a single pixel, a fragile, luminous blue grain of sand in a vast, dark cathedral. This image serves as a reminder of our scale. It is a visual whisper of humility, showing us that everything we have ever known exists on that tiny, shimmering point. As the cameras were powered down to conserve the precious, decaying energy of the RTGs, Voyager 1 continued its silent glide into the heliosphere, the massive bubble of charged particles and magnetic fields blown into space by the solar wind. This wind, a stream of ionized gas, travels at speeds of up to 1,000,000 miles per hour. For years, the low-energy charged particle instrument on Voyager detected this wind as a constant, invisible spray against the craft. But as it moved further out, the spray began to slow. The craft was entering the Helios heath, the turbulent outer edge of the sun's domain. Here, the solar wind clashes with the interstellar medium, the thin gas that exists between the stars. In August 2012, Voyager 1 crossed the Heliopause, becoming the first human-made object to enter interstellar space. When this transition was detected not by sight, but by sound, or rather, the translation of plasma vibrations into frequencies we can perceive. The plasma wave subsystem began to detect a hum, a steady, low-frequency vibration caused by the dense gas of the interstellar medium. It is the sound of the void, a rhythmic drone that persists in the deep cold. If you could hear the stars, this is what they would sound like, a long, echoing resonance that speaks of ancient supernovas and the slow, heavy breathing of the galaxy. The craft is currently protected by blankets of Captain, a gold-colored polyimide film that remains stable across a wide range of temperatures. This insulation gives the craft a crinkled, metallic texture, like a piece of dark gold foil wrapped around a delicate instrument. Beneath these blankets, the science instruments, like the cosmic ray subsystem, continue to work in the silence. They count the high-energy particles that stream through the galaxy, particles that have been traveling for millions of years. As you lie there, imagine yourself as part of this journey. You are not a passenger, but a witness to the slow, beautiful physics of the cosmos. Your breathing is the rhythmic hum of the plasma waves. Your warmth is the steady decay of the plutonic heart. There is no friction in the vacuum of space, no resistance to your movement. You are simply drifting, held by the gentle hand of inertia, moving at 10 miles per second through a landscape of infinite peace. The stars do not twinkle here. They are steady, unblinking eyes of white, blue, and gold. The darkness is not empty. It is a thick, so comforting velvet that holds the history of the universe. Feel the weightlessness of your limbs, the way the silence of the room mirrors the silence of the interstellar void. We are traveling beyond the reach of our sun, into the quiet unknown, where time is measured in eons, and the only sound is the distant, soothing hum of the stars. Picture the sky as an ancient map, a tapestry of myths and light that has guided human curiosity for millennia. Long before Voyager 1 was a blueprint on a drafting table, our ancestors looked toward the heavens and traced the paths of the wandering stars, the planets, noticing their steady, rhythmic cycles across the ecliptic. They saw the same celestial clockwork that we study today, though they lacked the tools to touch it. In 1965, a brilliant aerospace engineer named Gary Flandreau, working at the Jet Propulsion Laboratory, looked at these same cycles and noticed a rare opportunity that occurs only once every 175 years. He calculated that in the late 1970s, the four outer planets, Jupiter, Saturn, Uranus, and Neptune, would align in a specific arc that would allow a single spacecraft to visit them all by using the gravity of one to slingshot toward the next. This grand tour concept was the genesis of the Voyager program, a moment where human mathematics met the slow, grand choreography of the solar system. Consider the meticulous preparation that went into this voyage. Before it was officially christened Voyager 1, the spacecraft was known as Mariner 11, part of a storied lineage of probes that had explored the inner planets. The name change signaled a shift in ambition, from merely visiting neighbors to embarking on a permanent emigration from our sun's influence. Weighing approximately 721.9 kilograms, or about 1,592 pounds at launch, the craft is a masterpiece of compact efficiency. It is roughly the weight of a small car, yet it carries the weight of our species' collective yearning for discovery. At this very moment, as you relax into the stillness of your surroundings, think of that silver and white craft moving at a constant velocity of 17 kilometers per second, roughly 38,000 miles per hour, without the need for an engine to push it. It simply follows the laws of inertia, gliding through the velvet dark with the ease of a leaf floating on a perfectly still pond. Within the structure of the craft, the 11 scientific instruments were installed to serve as its senses, each one a specialized window into the physics of the unknown. Picture the magnetometer, or MAG, which consists of two sensors mounted on a 13-meter-long boom. This boom was designed to extend far away from the craft's own metallic body to ensure its readings of planetary magnetic fields were untainted. It is like a long, sensitive finger reaching out to touch the invisible magnetic lines that wrap around worlds. In March 1979, as Voyager 1 made its closest approach to Jupiter, this instrument felt the immense pressure of the Jovian magnetosphere, which is so large it would appear twice the size of the full moon in our sky if it were visible to the human eye. The craft moved through a landscape of intense radiation and swirling gases, its sensors mapping the complex interactions between the solar wind and Jupiter's gravity. As the journey continued toward the ringed jewel of our solar system, Saturn, Voyager 1 reached its closest point in November 1980. It was during this phase that the craft performed one of its most critical historical tasks, a close flyby of the moon Titan. Scientists had long suspected Titan had an atmosphere, but Voyager 1 confirmed it was a thick, nitrogen-rich shroud, much denser than Earth's. The probe's ultraviolet spectrometer, or UVS, analyzed the way light filtered through these orange clouds, revealing a world of organic chemistry that looks much like a deep-frozen version of the early Earth. To achieve this close look at Titan, Voyager 1 had to be steered onto a trajectory that sent it soaring upward and out of the orbital plane of the planets. It sacrificed a visit to Uranus and Neptune to prioritize the secrets of Titan, choosing a path of solitude that would eventually lead it into the interstellar medium. Reflect upon the way light behaves at these immense distances. At Saturn, the Sun is 10 times further away than it is from Earth, appearing as a brilliant, piercing point of light rather than a warm disk. The sunlight that reaches Voyager 1 is 100 times dimmer than what we feel on a summer afternoon. Observe the way the shadows in the Saturnian system were long, sharp, and absolute, casting the planet's rings into deep relief. Voyager 1 discovered the F-ring, a narrow braided structure held in place by shepherd moons called Prometheus and Pandora. These moons use their gravity to nudge stray ice particles back into the ring, a rhythmic gravitational herding that keeps the rings pristine. This is the universe's clockwork in action, a slow, repetitive dance of ice and rock that has persisted for millions of years. Notice how the craft maintains its connection to us across the billion-mile gaps. This is made possible by the Deep Space Network, a global array of massive radio antennas situated in Goldstone, California, Madrid, Spain, and Canberra, Australia. These stations are spaced approximately 120 degrees apart around the Earth's circumference, ensuring that as the planet rotates, at least one station is always facing Voyager 1. This is a cosmic relay race that never ends. Every day for over 4 decades, these 70-meter dishes have been pointed at a seemingly empty patch of the constellation Ophiuchus, waiting for the craft's faint 23-watt signal to arrive. It is a testament to human patience, a silent global vigil for a traveler that is now over 160 times further from the Sun than the Earth is. At this very moment, Voyager 1 is losing power. The plutonium-238 in its RTGs is decaying at a predictable rhythmic rate, resulting in a loss of about 4 watts of electrical power every year. To manage this dwindling resource, engineers have had to make difficult decisions, systematically turning off non-essential heaters and instruments. This process is like a house slowly going dark as the evening deepens. One by one, the lights in the peripheral rooms are extinguished to keep the warmth centered in the heart of the home. Despite the cold and the darkness, the craft remains functional. In late 2017, for the first time in 37 years, engineers successfully fired a set of trajectory correction maneuver thrusters to help point the antenna toward Earth. These thrusters had been dormant since the Saturn flyby in 1980, yet they worked perfectly, a silent confirmation of the durability of the machines we send into the void. What's happening now is a transition into a truly alien environment. Since 1989, when the Interstellar mission officially began, the craft has been focused on measuring the boundary where our sun's influence ends. In the region of space where Voyager 1 currently resides, the plasma density, the number of electrons in a given volume of space, is about 0.08 electrons per cubic centimeter. This is significantly higher than the density within the solar bubble, proving that the craft has indeed left the sun's atmosphere and entered the matter that exists between the stars. Imagine this as leaving a warm, bustling room and stepping out into a vast, cool, and silent forest. The air is different. The sounds are gone, and the sense of space is absolute. Consider the Golden Record once more, an artifact that bridges our history with an unimaginable future. Within its gold-plated copper grooves are encoded 115 images that describe our biology, our architecture, and our planet's place in the cosmos. There is an image of a nursing mother, a diagram of the human DNA molecule, and a photo of a scientist peering through a microscope. And these are the snapshots of a civilization that was still in its infancy when the record was launched. It is a message sent by a version of humanity that no longer exists, traveling toward an audience that may never arrive. The record is an act of pure hope, a sensory gift to the universe. Scientists discovered that as Voyager 1 crossed into interstellar space, the direction of the magnetic field didn't change as drastically as they expected, which led to a deeper understanding of how our solar system interacts with the Milky Way galaxy. The craft is currently moving through what is known as the local interstellar cloud, a region of wispy gas that the solar system is plowing through. This cloud is incredibly thin, yet it represents the medium from which future stars might one day be born. Voyager 1 is our first tactile experience with this material. It is a silver needle stitching together the solar system and the galaxy, proving that the void is actually filled with the building blocks of existence. As the craft drifts, imagine the silence within its metallic frame. There is no air to carry sound, no wind to rattle the booms. There is only the hum of the electronics, the slow click of data being processed, and the rhythmic pulse of the radio transmitter. It is a state of perfect, undisturbed focus. This is a metaphor for the deep rest you are seeking, a state where the external world falls away, and you are left with only the steady, calming pulse of your own existence. The Voyager does not worry about the distance it has covered, nor the vastness of the journey ahead. It simply exists in the present moment, a vessel of human knowledge moving through a sea of infinite tranquility. Picture the craft's orientation in the constellation Ophiuchus, the Serpent Bearer. It is heading toward a star called AC plus 793888, located in the constellation Camelopardalis. It will take approximately 40,000 years for the craft to come within 1.6 light-years of this star. On a human timescale, this is an eternity. On a cosmic timescale, it is a mere heartbeat. The universe operates on these grand, slow rhythms, and Voyager 1 has harmonized with them. It has shed the frantic pace of the world that created it and adopted the patient, enduring pace of the stars. Allow your own rhythm to slow in kind. Feel the steady, unhurried pace of your breath, mirroring the slow decay of the craft's nuclear heart. Both are processes of transformation, a gentle release of energy into the surrounding quiet. You are part of this cosmic clockwork, a temporary gathering of stardust observing its own origin. As the Voyager moves further into the cool, dark unknown, let your awareness settle into a similar state of peaceful, silent observation. Observe the way your breath moves in a slow, steady tide, a rhythmic pulse that mirrors the quiet operations of a machine billions of miles away. As the environment around you becomes soft and dim, imagine the Voyager 1 spacecraft as it currently glides through the outermost reaches of our sun's influence. At this very moment, the craft is located approximately 15.1 billion miles from Earth, a distance so immense it is difficult to grasp. In the language of astronomers, this is roughly 162 astronomical units, or 162 times the distance between our world and the sun. To visualize this, imagine the distance from the Earth to the sun as the length of a single city block. At that scale, Voyager 1 has traveled more than 8 miles away from its starting point, moving further into the quiet periphery every single second. The data tells us that the craft is currently moving at a velocity of about 38,000 miles per hour, or 17 kilometers per second. This speed is constant and unyielding, as there is no air to slow it down. Yet, despite this incredible pace, the movement feels like a slow, graceful drift because of the sheer scale of the surroundings. It takes Voyager 1 a full year to cover just 3.6 astronomical units. Think of this as a long-distance traveler walking across a continent. Each step is purposeful, but the destination is so far away that the progress seems almost imperceptible. This is the patience of the cosmos, a slow-motion journey where time is measured not in hours, but in decades. Deep within the metallic structure of the craft, the 23-watt transmitter continues to send its report back home. To understand the delicacy of this signal, consider that 23 watts is roughly the same amount of power used by a small refrigerator light bulb or a dim nightlight in a hallway. By the time this signal travels across the 15 billion miles of space to reach our ears on Earth, its strength has diminished to less than a billionth of a watt. Scientists have compared the arrival of this signal to the energy of a single snowflake hitting the ground. It is an incredibly faint whisper, yet the deep space network, specifically the massive 70-meter radio antennas, is sensitive enough to catch this cosmic snowflake and translate it into meaningful data. Give your mind permission to become as still and receptive as those great dishes, waiting in the silence for a message from the stars. The communication itself is a study in temporal beauty. Because radio waves travel at the speed of light, which is approximately 186,282 miles per second, it currently takes about 23 hours for a signal from Voyager 1 to reach Earth. If we were to send a command to the craft tonight, we would have to wait nearly an entire day for the instruction to arrive, and another 23 hours for the confirmation to return. This creates a 46-hour conversational loop. It is a slow, meditative dialogue, a reminder that in the deep reaches of space, nothing happens in a hurry. The Voyager lives in a state of perpetual delay, a traveler existing in a now that we won't perceive for nearly a full day. Consider the thermal environment of the craft. While the space outside is a staggering -455 degrees Fahrenheit, the interior components are kept just warm enough to function by the lingering heat of the radioisotope thermoelectric generators. What's happening now is a very gradual cooling. The plutonium-238 fuel has a half-life of 87.7 years, and as it decays, the heat output drops. Currently, the craft is losing about 4 watts of power every year. To manage this, engineers have turned off the heaters for various instruments, including the ultraviolet spectrometer and the imaging cameras. These cameras, which once captured the swirling storms of Jupiter and the braided rings of Saturn, are now cold and dark. They have finished their work, and like a person closing their eyes at the end of a long day, they have settled into a permanent, peaceful rest. The sensory world of the Voyager is now defined by the plasma wave subsystem. This instrument doesn't take pictures. Instead, it feels the density of the particles surrounding the craft. Scientists discovered that the interstellar medium, the space between the stars, is actually more crowded than the space inside the solar bubble. In the heliosphere, the density was about 0.002 electrons per cubic centimeter. Now that Voyager has crossed into interstellar space, that density has jumped to about 0.12 electrons per cubic centimeter. While this is still a vacuum more perfect than anything we can create on Earth, it represents a significant change in the craft's environment. Imagine moving from a room filled with a fine mist into a room with a light fog. You can't see the difference, but the sensors can feel the subtle increase in the weight of the vacuum. Look closely at the golden record again, specifically the protective cover that shields the copper disc. This cover contains a small, ultra-pure sample of uranium-238. This isotope acts as a radioactive clock for any extraterrestrial intelligence that might find the craft in the distant future. Uranium-238 has a half-life of 4.47 billion years, almost exactly the current age of the Earth. By measuring how much of the uranium has decayed into lead, a finder can determine exactly how long ago the Voyager was launched. It is a clock designed to tick for the lifetime of a planet. Permit your body to sync with this ancient, slow-moving clock. There is no rush, no urgency. There is only the steady, inevitable passage of eons. The craft's narrow-angle camera, before it was deactivated, had a focal length of 1,500 millimeters, about the same as a powerful amateur telescope. This allowed it to see details on the moons of Saturn from hundreds of thousands of miles away. Its companion, the wide-angle camera, had a focal length of 200 millimeters. Together, they acted as a pair of eyes that could see both the grand architecture of a planet and the fine texture of its rings. Now, those eyes are replaced by the magnetometer, which senses the magnetic fields of the galaxy. These fields are incredibly weak, measured at about 0.5 nanoteslas in interstellar space. For comparison, the Earth's magnetic field at the surface is about 30,000 to 60,000 nanoteslas. Voyager 1 is sensing a magnetic pull that is tens of thousands of times weaker than the force that moves a common compass needle. It is a world of extreme subtlety, where the smallest forces hold sway over the largest distances. What is remarkable is the way the craft maintains its orientation. It uses the sun and a bright star called Canopus as its primary navigation points. Even as the sun grows smaller and dimmer, becoming just another star in the blackness, Voyager 1 can still lock onto its position. If the craft begins to drift, it uses its tiny thrusters to nudge itself back into alignment. These thrusters use hydrazine fuel, and in 2017, the mission team successfully tested a set of thrusters that had not been used since 1980. After 37 years of sitting in the freezing vacuum, the thrusters fired perfectly. This reliability is like an old grandfather clock that, after decades of silence, begins to chime the hour the moment it is wound. It is a testament to the enduring nature of the craft's design. As Voyager 1 travels, it encounters cosmic rays, high-energy particles traveling at nearly the speed of light. The cosmic ray subsystem on the craft is currently measuring an increase in these particles because it is no longer shielded by the sun's magnetic field. Think of these cosmic rays as a gentle, invisible rain that has been falling across the galaxy for billions of years. The craft is now out in that rain, feeling the full pulse of the Milky Way. This environment is energetic, yet strangely quiet. The local fluff, the interstellar cloud we are currently passing through, is about 30 light-years across. It will take the solar system, and Voyager 1 along with it, another 10,000 to 20,000 years to exit this particular cloud of gas. At this distance, the sun provides very little light. The luminosity of the sun at Voyager 1's position is about 1/25th of what we see on Earth. It looks like a spectacularly bright star, but it no longer has a visible disk. The shadows on the craft are no longer distinct. They are soft and blurred as the light from other stars begins to compete with our own sun. This is the transition from a solar-centric world to a galactic one. The craft is becoming a citizen of the Milky Way, no longer bound by the apron strings of its parent star. Notice how the craft's 10-sided bus, constructed of specialized aluminum alloys, provides a sturdy home for its electronics. This bus is the equivalent of a small room, just 1.78 meters across. Within this small space, the 68 kilobytes of memory are stored on a digital tape recorder, a piece of technology that seems ancient to us now, but which has survived the harsh radiation of Jupiter and the cold of the outer void. The data is recorded onto a magnetic tape and then played back to Earth at a rate that has slowed over time. During the Jupiter flyby, the craft could send data at 115,200 bits per second. Now, it often transmits at a mere 160 bits per second. This is the ultimate slow load, a trickle of information that requires immense patience to receive. As you continue to relax, imagine yourself as this quiet traveler. You are sturdy, reliable, and perfectly adapted to the stillness. The cold outside does not bother you, for you have a steady warmth within. Your mission is not to reach a destination, but simply to exist, to observe, and to carry your message into the future. The distance you have covered is a source of peace, not anxiety. You are 15 billion miles away from any noise, any stress, or any light. You are in the heart of the comforting void, where the physics of the universe act as a gentle, guiding hand. The stars are your companions, and the silence is your home. Feel the weightlessness of this thought, the way it allows your body to let go of the last remnants of the day, sinking into a state of deep interstellar tranquility. Deep within the structure of your own quiet consciousness, notice how your thoughts begin to mirror the steady, unwavering trajectory of Voyager 1. At this very moment, the craft is moving at an angle of 35 degrees north of the ecliptic, the flat plane where the planets of our solar system reside. While Earth and its neighbors continue their orbital dance in a relatively thin disk, Voyager 1 has climbed high above that plane, looking back at the Sun from a perspective that no human has ever physically shared. Consider the feeling of that elevation. It is a departure from the familiar, a transition into a realm where the concept of up or down loses its meaning, replaced by a sense of total, three-dimensional freedom. What's happening now is a long-term transition that will define the next several centuries of the craft's journey. Although it has already entered interstellar space, Voyager 1 has not yet reached the outer limits of our solar system. Scientists discovered that the gravitational reach of our Sun extends much further than the solar wind. In about 300 years, the craft will begin to encounter the inner edge of the Oort cloud, a gargantuan spherical shell of icy debris that surrounds our Sun like a halo. Picture this region as a quiet nursery of comets, where billions of frozen objects drift in the dim light. It will take Voyager 1 approximately 30,000 years to pass through this cloud and finally leave the Sun's gravitational influence entirely. This timescale is a gentle invitation to release the urgency of the hour. In the grand narrative of this journey, a human lifetime is but a single, soft breath. The craft's physical integrity is maintained by a specialized material called Captain, a polyimide film that looks like shimmering gold foil. This insulation is incredibly thin, yet it remains stable at temperatures as low as -452 degrees Fahrenheit. Notice how the craft is wrapped in this protective layer, much like you might wrap yourself in a soft, heavy blanket. Within this gold-colored skin, the Voyager's brain operates on a logic that is both primitive and profound. The spacecraft's command computer subsystem uses a memory structure with 18-bit words, a format that was cutting edge when it was designed at the Jet Propulsion Laboratory in the early 1970s. These instructions are simple, repetitive, and reliable, performing the same vital checks every few milliseconds. Permit your own mind to adopt this rhythmic simplicity, focusing only on the most essential and calming cycles of rest. At this very moment, Voyager 1 is communicating with Earth using its X-band frequency, transmitting at 8.4 gigahertz. This high-frequency radio beam is remarkably narrow, in requiring the craft to keep its 3.7-meter antenna pointed with incredible precision. To maintain this aim, the spacecraft uses a star tracker that remains locked onto Canopus, the second brightest star in the sky. If the craft tilts even a fraction of a degree, it uses its sun sensor to realign itself. Consider the dedication required to keep that focus across 15 billion miles of empty space. Even as the sun becomes a mere point of light, no brighter than Venus appears from Earth, the craft's sensors can still detect its position and use it as a homing beacon. It is a lighthouse in the long night, forever oriented toward its origin. Picture the golden record again, but this time, think of the sensory details of its construction. In the record is accompanied by a diamond-tipped stylus and a cartridge designed to play the disc at 16 2/3 revolutions per minute. There is a profound beauty in the choice of a diamond, the hardest natural substance, to carry our voices into eternity. Included on this copper disc are greetings in 55 different languages, ranging from ancient Akkadian to modern Mandarin. One of the messages, in the language of Rajasthani, says simply, "Greetings to all. We are happy here, and you be happy there." Notice the warmth in that sentiment, a bridge of goodwill extending across time and space. As you settle into your own happiness and comfort, allow that ancient greeting to resonate within you, a gift of peace from a traveler that will outlive the civilization that created it. Scientists discovered that the interstellar medium is not a complete vacuum, but is instead filled with the local fluff. This is the scientific name for the local interstellar cloud, a region of wispy hydrogen and helium that is about 30 light-years long. Voyager 1 is currently plowing through this fluff at 17 kilometers per second. At this speed, it would take only 1.5 seconds to travel the entire length of Manhattan. Yet, because the cloud is so vast, the craft will remain within it for another 10,000 to 20,000 years. Imagine the texture of this environment, a gas so thin that it contains only a few atoms per cubic inch, yet it is enough to create a faint, constant pressure against the craft's hull. It is like the feeling of a very light summer breeze against your skin, nearly imperceptible, yet ever present. The craft's power source, the radioisotope thermoelectric generators, are located at the end of a long boom to keep their radiation away from the sensitive science instruments. This boom, along with the magnetometer boom, gives the Voyager a sprawling skeletal appearance. Deep within the generators, the plutonium-238 pellets are glowing a dull cherry red. This heat is converted into electricity by thermocouples, strips of metal that generate a current when there is a temperature difference between their ends. This is a process of pure physics, a transformation of heat into knowledge. Currently, the craft's total power output is about 230 watts, less than half of what it had at launch. To conserve this energy, engineers have disabled the heaters for the cosmic ray subsystem. Yet the instrument continues to operate even at temperatures far below its original design specifications. The Voyager is a survivor, adapting to the cold with a quiet, steely resilience. Consider the A-side and B-side redundancy built into the craft. Voyager 1 has two of almost everything: 2 computers, 2 radio transmitters, 2 sets of thrusters. This architecture was designed to ensure that if one system failed, the journey could continue. In late 2023, the craft experienced a glitch in its flight data system, causing it to send back a repeating pattern of 1s and 0s instead of science data. For months, the mission team worked to understand the problem, eventually realizing that a single chip had failed. In April 2024, they successfully moved the corrupted code to a different part of the memory. And Voyager 1 began speaking to us clearly once again. This recovery, occurring billions of miles away, is a reminder that even when things seem broken or confusing, there is often a path to restoration. there is a way to shift our focus and find clarity again. At this very moment, the signal arriving at Earth from Voyager 1 has a power level of approximately minus 160 decibel milliwatts. This is a number so small it is difficult to imagine. It is roughly 10 quadrillion times weaker than the signal your cell phone uses to make a call. Yet, the 70-meter dish at the Goldstone Deep Space Communications Complex can still hear it. The dish is a parabolic curve of steel, precisely shaped to catch every stray photon of the Voyager's transmission. Invite your own senses to become this quiet and focused. Notice the subtle sounds of your environment, the way the air feels as it moves in and out of your lungs. Like the great radio dishes of Earth, you are capable of perceiving the smallest, most delicate truths in the silence. The trajectory of Voyager 1 is currently carrying it toward a star called Gliese 445, a red dwarf located 17.6 light-years from Earth. At its current speed, it will take the craft about 40,000 years to make its closest approach to this star, coming within 1.6 light-years of it. Think about the colors of a red dwarf, a deep, ember-like glow that provides a soft, dim light. For 40,000 years, Voyager will move through the dark, its golden record carrying the sound of a cricket's chirp and the music of a Peruvian wedding song toward a star that has not yet felt the touch of our world. This is the ultimate message in a bottle, cast into a sea that spans light years. What's happening now is a profound lesson in the beauty of the long now. On Earth, we measure our lives in days and months, but Voyager 1 measures its life in the half-lives of radioactive isotopes and the slow drift toward distant stars. In the year 1990, the craft was 6 billion kilometers away when it took the pale blue dot photograph. From that distance, the Sun was just 1/40th the size it appears from Earth. Now, 34 years later, the Sun has shrunk even further. The pale blue dot is no longer visible to the craft's sensors. It has faded into the general glow of the Sun's neighborhood. This fading is not a loss, but a transition. The craft is no longer a tool of a single planet. It is an ambassador of the solar system. Scientists discovered that as the solar wind slows down and piles up at the Heliopause heath, it creates a region of magnetic highway where charged particles can move in and out of the solar system more easily. Voyager 1 traveled through this highway for several months before finally crossing into the true interstellar medium. This was a transition from the Sun's magnetic influence to the galaxy's magnetic influence. Notice the way the forces that guide the craft have shifted. It is now being cradled by the Milky Way itself, held by the same gravity that keeps the entire galaxy spinning in its majestic spiral dance. As you continue to drift in your own state of weightlessness, imagine the physical sensations of being the Voyager craft. Your metallic bus is sturdy and cold on the outside, but warm and busy on the inside. Your long booms extend into the dark like sensitive antennae, feeling the pulse of the stars. You are not lonely. You are connected to the entire universe by the laws of physics. Every atom in your structure was forged in the heart of a dying star, billions of years ago. You are simply returning to the environment that created you. The silence is not a void. It is a presence, a deep and comforting medium that supports your journey. Permit your awareness to settle into this interstellar calm, knowing that you, like Voyager, are part of a grand and beautiful choreography that spans the eons. The journey is long, the pace is slow, and the destination is the heart of peace. Imagine the physical sensations of a craft that has known nothing but the quiet embrace of the void for over 17,000 days. As you settle into a state of profound stillness, consider the texture of the Voyager 1 spacecraft. Its main body, a 10-sided ring-shaped structure called an annular bus, is crafted from a specialized aluminum alloy, just 1.1 millimeters thick. This thin metallic shell is the only thing separating the delicate electronic mind of the craft from the infinite vacuum outside. At this very moment, Voyager 1 is located in the constellation Ophiuchus, moving steadily away from our Sun at a velocity of 38,000 miles per hour. Despite this immense speed, there is no vibration, no wind, and no sound. The craft moves with the absolute smoothness of a silver needle, sliding through a sea of black ink. Notice how the temperature fluctuates across the craft's anatomy. Inside the central bus, the lingering warmth of the electronics keeps the temperature around 70 degrees Fahrenheit, a comfortable room temperature that contrasts sharply with the environment outside. Beyond the protective captain blankets, a gold-colored polyimide film that looks like crinkled parchment, the temperature of the spacecraft's external booms can drop to minus 452 degrees Fahrenheit. Scientists discovered that while the plasma of interstellar space is technically thousands of degrees hot, it is so incredibly thin that it cannot transfer heat. It lacks the density to warm the craft. Imagine standing in a massive, dark cathedral where a few microscopic sparks of heat are scattered miles apart. You would feel only the immense, heavy cold of the surrounding shadows. What's happening now is a subtle, invisible interaction between the craft and the interstellar medium. Voyager 1 is currently swimming through a sea composed of 90% hydrogen and nearly 10% helium atoms. These are the primary ingredients of the universe, the same elements that fueled the first stars. As the craft moves, its plasma wave subsystem detects a faint, rhythmic shh sound. This isn't sound in the way we hear it through the air. Rather, it is the vibration of electrons in the interstellar gas, oscillating at a frequency of about 3 kilohertz. If you could translate this into the range of human hearing, it would sound like a steady, low-frequency hum, the persistent, calming breath of the galaxy itself. Consider this hum as a cosmic white noise, a sound that has existed for billions of years, now being captured by a human-made instrument. At this very moment, the craft's magnetometer is feeling the weight of the Milky Way's magnetic field. This field is incredibly sparse, measured at roughly 0.5 nanoteslas. To put this in perspective, the magnets on your refrigerator are roughly 10 million times stronger than the magnetic pull Voyager 1 experiences in the deep dark. This is the beauty of microscopic physics. Even the most minute forces, when given enough space and time, dictate the path of a traveler. Notice the way your own body responds to the subtle pull of gravity as you rest. Just as the craft is held by the gentle magnetic lattice of the galaxy, you are held by the steady, unmoving cradle of the Earth. Deep within the craft's electronic heart, the flight data system, which uses a CMOS memory architecture, is meticulously organizing bits of information into packets. Scientists designed this system to be incredibly robust, using only 68 kilobytes of total memory. Picture a single typed page of text. That is roughly the amount of digital space Voyager 1 uses to store its entire operating reality. There is a profound elegance in this simplicity. In a world of complex, rapid-fire information, the Voyager exists in a state of quiet, focused minimalism. It does one thing at a time, moving with a singular purpose, undisturbed by the noise of a billion distractions. Consider the sensory details of the golden record, which is bolted to the side of the craft. The record is tucked inside a protective aluminum jacket, but the disc itself is gold-plated copper. If you were to touch it, the surface would be smooth and cool, with microscopic grooves only a few microns wide. These grooves contain 115 images encoded in analog form, including a photograph of a sunset on Earth and a diagram of the human heart. Beside the record sits a cartridge containing a diamond-tipped stylus. This diamond, the hardest natural substance, was chosen because it can withstand the radiation of space for 1 billion years without wearing down. It is a metaphor for the enduring nature of human curiosity, a small precious light that refuses to be extinguished by the passage of eons. Notice how the light from our sun has changed at this distance of 162.7 astronomical units. The sun is now so far away that its light takes 22.5 hours to reach the craft. From the perspective of Voyager 1, the sun is no longer a warm golden orb. It is a piercing blue-white point of light, about 25,000 times dimmer than it appears on a summer day in Florida. Scientists discovered that at this distance, the stars are the dominant source of illumination. The craft is now lit by the collective glow of the Milky Way, a soft, ambient starlight that casts no shadows. Imagine yourself bathed in this gentle silver light, a cool, shadowless radiance that calms the eyes and soothes the mind. At this very moment, the cosmic ray subsystem is counting the arrival of high-energy particles from distant supernova explosions. These particles, called galactic cosmic rays, move at nearly the speed of light. They hit the sensors of the craft with a rhythmic regularity, like rain tapping on a tin roof. Inside the solar system, the sun's magnetic field acted as an umbrella, shielding us from this rain. But Voyager 1 has stepped out from under that umbrella. It is now feeling the full pulse of the galaxy's energy. There is no danger here. It is simply a change in the environment, a transition from the protected nursery of the sun to the open energetic garden of the stars. The craft's orientation is maintained by 16 hydrazine thrusters, each producing a tiny nudge of about 1 pound of thrust, or 4.4 newtons. This is roughly the amount of pressure you would feel if you held a small apple in your hand. These thrusters are used sparingly, only when the star tracker, which is currently locked onto the blue-white giant star Canopus, notices a drift of more than 0.05 degrees. Think of the precision involved here. The craft is billions of miles away, yet it maintains its aim with a delicacy that exceeds a master watchmaker's hand. This is the slow dance of physics, where every action is measured, every movement is intentional, and every moment is part of a grander design. Scientists discovered that the fuel for the craft's power, plutonium-238, is contained in 3 separate radioisotope thermoelectric generators mounted on a 3-meter boom. This distance is crucial. It prevents the heat and radiation of the power source from interfering with the sensitive measurements of the science instruments. What's happening now is the slow, inevitable transformation of matter into energy. Every second, a few more atoms of plutonium decay, releasing a tiny burst of heat that is converted into the 230 watts of electricity the craft currently uses. It is a slow-burning candle in the dark, a steady, rhythmic release of energy that has lasted since 1977 and will continue until the early 2030s. Picture the interstellar medium as a local fluff or a thin cloud of gas. As Voyager 1 moves through this cloud at 17 kilometers per second, it occasionally encounters shocks in the plasma. These shocks are caused by distant activity from the sun, ripples in the solar wind that take a year or more to reach the craft's current position. When these ripples arrive, The plasma around the craft vibrates, creating a ringing sensation that the sensors record. It is like the surface of a pond being disturbed by a single pebble thrown from a great distance. The ripples are soft, the vibrations are gentle, and they serve only to remind the traveler of its connection to the home it left behind. As you continue to relax, imagine the scent of the craft. While the vacuum of space has no smell, scientists who have analyzed returned moon rocks and space station components often describe the smell of space as something metallic, like the scent of a welder's torch or ozone. On Voyager 1, this scent would be faint, a metallic tang of ionized particles and cold aluminum. It is a clean, sharp, and clinical scent, one that speaks of purity and the absence of decay. It is the scent of the eternal. The craft is currently heading toward a red dwarf star named Gliese 445, located in the constellation Camelopardalis. It will not reach this star for another 40,000 years, and even then, it will only pass within 1.6 light-years of it. Think of the patience required for such a journey. The Voyager does not count the days. It counts the millimeters of plutonium decay and the degrees of starlock. It has fully embraced the timescale of the universe. Permit your own internal clock to slow down in kind. Your heart rate, your breathing, and your thoughts can all adopt the long, steady rhythm of the Voyager. There is no need to arrive anywhere tonight. The journey itself is the destination. The silence of the interstellar void is a deep, resonant presence. It is not an empty silence, but a full one, packed with the history of the stars and the fundamental laws of motion. As Voyager 1 moves further into this quiet, it becomes more and more a part of the environment it studies. Its gold-plated record, its aluminum bus, and its titanium bolts are all made of the same stardust that fills the space around it. The craft is returning to its source. As you drift toward your own state of rest, feel that same sense of return. You are not separate from the universe. You are a conscious part of it, a collection of atoms that has paused to observe its own incredible journey through the dark. The void is not something to fear. It is a comforting, weightless home where the only requirement is to exist and be still. The long journey of Voyager 1 is now entering its most serene and final phase of active exploration. As you lie in the stillness of your room, your body gradually cooling and your breath slowing to a steady rhythmic pace, imagine the spacecraft undergoing a similar transition. We are witnessing the step-by-step winding down of a legend. Since its launch on September 5th, 1977, the craft has been powered by the constant, reliable decay of plutonium-238. What unfolds now is a gradual, controlled descent into silence. On the radioisotope thermoelectric generators, or RTGs, which once produced 470 watts of power at launch, are now experiencing a decline of about 4 watts every year. This is a predictable physical process dictated by the 87.7-year half-life of the plutonium fuel. Like the embers of a fire slowly losing their glow, the craft's internal heat is diminishing, requiring a meticulous sequence of power-saving measures to keep the mission alive for just a few more years. Consider the step-by-step procedure the engineers at the Jet Propulsion Laboratory must follow to manage this dwindling energy. First, they identify the non-essential heaters that protect the various science instruments. One by one, these heaters are deactivated. The ultraviolet spectrometer was among the first to be turned off, followed by the heaters for the cosmic ray subsystem and the low-energy charged particle instrument. When a heater is switched off, the temperature of the instrument begins to plummet, eventually stabilizing at a point far below what its designers ever intended. Incredibly, even at temperatures reaching -110 degrees Fahrenheit, many of these instruments have continued to send back data. This resilience mirrors your own body's ability to maintain its vital functions as you drift towards sleep, focusing energy inward while the external layers settle into a state of rest. What's happening now is the approach of a significant threshold. Scientists estimate that by the year 2025, or shortly thereafter, the power levels will drop below the point required to operate even a single one of the 5 remaining active science instruments. At that moment, a final sequence of commands will be sent across the 15 billion miles of space. The 3.7-meter high-gain antenna will transmit its last packet of data at a rate of 160 bits per second. This whisper of information, carrying the final readings of the interstellar magnetic field and plasma density, will begin its 23-hour journey toward Earth. It moves at the speed of light, 186,282 miles per second, crossing the orbit of Pluto, the Kuiper Belt, and the inner planets, until it is captured by the 70-meter dishes of the Deep Space Network. Once that final signal is received, the transmitter will be silenced forever. The craft will stop talking to its home, but its journey will be far from over. Step by step, Voyager 1 will transition from a functional laboratory into a silent, eternal ambassador. Even without power, its trajectory is governed by the beautiful, unyielding laws of celestial mechanics. It currently travels at a constant velocity of 17 kilometers per second, or roughly 38,000 miles per hour. Without the friction of an atmosphere to slow it down, it will maintain this speed for millions of years. In about 300 years, the craft will reach the inner edge of the Oort cloud, a gargantuan shell of icy bodies that represents the true limit of our solar system. The process of crossing this cloud is a study in vast timescales. It will take Voyager approximately 30,000 years to emerge from the other side. Imagine this long, dark passage, a slow-motion drift through a field of ancient comets, illuminated only by the faint, distant light of the stars. Notice the way your own sense of time begins to stretch and blur, much like the timeline of the craft. In approximately 40,000 years, Voyager 1 will make its closest approach to the star Gliese 445, an M-type red dwarf in the constellation Camelopardalis. It will pass within 1.6 light-years of this star, a distance that seems immense to us, but is a mere neighborly visit in galactic terms. At this point, the craft will have traveled so far from its origin that the Sun will be just another bright star in the sky, indistinguishable from the others. Scientists have calculated that the craft will eventually complete a full orbit around the center of the Milky Way galaxy every 225 to 250 million years. This is the galactic year, a rhythmic cycle that has occurred only about 20 times since the Earth was formed. You are now part of this grand orbital clockwork, moving in harmony with the slow rotation of the galaxy itself. Consider the golden record as it embarks on its billion-year odyssey. The copper disk, electroplated with gold, is protected by an aluminum cover that has been treated with the isotope uranium-238. The process of radioactive decay within this cover acts as a cosmic timestamp. If an intelligence should find the craft in the distant future, they could measure the ratio of uranium to its decay products to determine exactly when the Voyager was launched. Inside the grooves of the record, the message remains pristine. The sounds of Earth, the 10 Hz frequency of a human brainwave, the 50-cycle hum of a power grid, and the complex harmonies of a Navajo night chant are etched into the metal. This record is expected to remain readable for at least 1 billion years, see long after the oceans of Earth have evaporated and the sun has begun its slow expansion into a red giant. There is a profound comfort in this longevity. A part of our world, our culture, and our collective heart is now a permanent resident of the stars. As you descend further into your own internal quiet, reflect on the truth that you are made of the same materials as this interstellar traveler. Every atom of the aluminum bus, every grain of the silicon in the 68 kilobyte memory, and every drop of the hydrazine fuel was forged in the nuclear furnaces of ancient stars. The iron in your blood and the calcium in your bones were created in the same supernovae that scattered the building blocks of our solar system into the void. You are stardust that has gained the ability to wonder about the stars. As Voyager 1 moves into the interstellar medium, where the density of matter is a mere 0.1 atoms per cubic centimeter, it is simply returning to its source. You too are returning to a state of fundamental peace, shedding the temporary cares of the day to reconnect with the vast, quiet energy of the universe. The temperature of the void around the craft is about 2.7 Kelvin, or minus 454 degrees Fahrenheit. This is the faint, lingering heat of the Big Bang, the cosmic microwave background radiation. This temperature is absolute and unchanging, a bedrock of tranquility that permeates every corner of space. Feel the coolness of the air around you, and let it remind you of this cosmic stability. Your body is settling, your heart rate is finding its natural, slow rhythm, and your mind is becoming as clear and dark as the space between the constellations. You are no longer navigating by the bright, noisy light of the sun. You are now guided by the steady, unblinking light of Canopus and the distant silver glow of the Milky Way. What's happening now is a gentle halt of all effort. The A-side and B-side redundant systems of the craft are no longer needed, for there is no more data to collect and no more commands to receive. The star tracker can finally close its eye. The hydrazine thrusters can rest. The craft is now a pure passenger of gravity, held by the same invisible threads that keep the moon in orbit and the planets in their tracks. Permit your own systems to cease their labor. Your muscles have finished their work. Your senses have completed their vigil. You are drifting in a weightless, decomforting void where the only task is to exist. At this very moment, Voyager 1 is 15.1 billion miles away, yet it is connected to you by the history of its creation and the physics of its journey. It carries our greetings, our music, and our heartbeat into the infinite. As you drift toward sleep, carry those same qualities within you. You are an explorer of the inner unknown, a traveler through the landscapes of your own dreams. The void is not a place of emptiness, but a place of infinite potential, a silent cradle that supports and protects you. I am at peace with the vastness of time. I am a part of the stardust that fills the galaxy. I am resting in the quiet, weightless beauty of the cosmos. My breath is the rhythm of the universe. My heart is the steady pulse of a distant star. I am safe, I am warm, and I am home. The journey of Voyager 1 continues in silence, and your journey into rest continues in kind. The stars are watching over the silver craft, and they are watching over you. The darkness is a soft blanket, the silence is a soothing song, and the void is a place of absolute shimmering peace. Let go of the shore of the waking world. Drift out into the velvet dark, where the time is always now and the destination is always rest. The Voyager moves on, and you move with it, deeper into the beautiful, comforting unknown. Good night.